These are the work kinetic energy theorem problems from your packet. There are 3 of them. The first one talks about a 50-kilogram parachutist falling at a speed of 47 meters per second. When the parachute opens, the parachutist's speed upon landing is 5 meters per second. How much work is done by the air to reduce the parachutist's speed? All right, let's pull our variables out. We have a 50-kilogram parachutist, that is 50.0 kilograms, that is our mass, falls at a speed of 47 meters per second. That's going to be our initial speed, our initial velocity there, when the parachute opens. Okay, the parachutist speed upon landing, that's our final velocity, is 5 meters per second. Okay. How much work is done by the air to reduce the parachutist's speed? Before we talked about work being equal to force times distance. This time, work is equal to the change in kinetic energy. So work equals to the change, that's delta, KE. Or, what we can talk about is work equals to KEF minus KEI. That's final minus initial. And of course, kinetic energy is equal to 1/2 mv squared. All right, plugging this in here. We only have one mass, but we're going to assume that this guy falling out of through the sky is not going to change his mass. So our work is equal to 1/2. Our m is 50. Our final velocity here is 5. Make sure we square that. Minus 1/2, 50. And that is our initial velocity, 47 squared. Do some math. That's 625 minus 55,225. Those are both in kinetic energy, so they are in joules. And our work is equal to negative 54,600 joules. Negative. What does that negative mean? Okay, the negative means that he is slowing down. Okay, or the work is in the opposite direction as he's moving. All right, next one here. 450-kilogram compressor slides down a loading ramp that is 7 meters long, initially at rest. The compressor speed at the bottom of the ramp, 1.1 meters per second. What is the magnitude? What is the size of the net force acting on the compressor? All right, we are going to try to find our force. If we're trying to find our force, we're going to use our work kinetic energy theorem. To find our work, we have our distance, so we can do work equals force times distance and solve for force. It'll make sense as we go along here. So, using our information here, our mass, meters. Initially at rest, VI equals 0. VF at the bottom of the ramp. What is the magnitude of the net force? Okay, so we're looking for force equals. All right, first let's find our work. We'll plug it into work equals force times distance. We'll find our force. And we have work equals KEF minus KEI, so that is 1/2 450. Our final velocity here is 1.1. Make sure you square it, minus 1/2 450. Our initial velocity is 0. Okay, so that's whole thing here, 1/2 times 450 times 0, do it in your calculator. Guess what you're going to get? 0 minus, okay, and then that there is 272.25 joules. So our work equals 272.25 joules. All right, knowing what we know, we can do work equals force times distance. We'll plug that in there. So I'm going to erase this up here. distance is 7 meters. So our force equals 38.9. Since it's a force, it's going to be in newtons. All right, the last one and most fun one that we're going to have today. We have a hockey puck with an initial speed of 8 meters per second, coasts 45 meters to a stop across the ice. If the force of friction on the puck has a magnitude of 0.12 newtons, what is the puck's mass? Puck's traveling this way. If the puck's traveling this direction and slowing down, which direction is the force? If it's slowing down, it's going to be opposite the direction that it's going. That'll be important later. All right, let's pull our variables out. What we have here is we have an initial speed of 8.0 meters per second. We have a distance of 45 to a stop. That's the final velocity, 0. The force of friction, so that's our force that's going to act on this thing, on this puck. It's the force that's going to slow it down. It's 0.12 newtons. Okay, what is the puck's mass? Mass equals question mark. Now, you're already thinking, all right, if this thing's slowing down, and I know that force and distance have to be in the same direction. Well, yes. Okay. What is our direction? If our force is going that way, if our direction is going that way and our force is going this way, what's our angle? Okay, this and this, that's 180 degrees. So theta equals 180 degrees. If you have a question about that, go ask Coach Burrow. He'll explain it. Okay, we have work equals force d cosine theta. Just one of our formulas. We're going to use that and we're going to plug it in to what we have. Okay, we're going to use the kinetic energy theorem, the work kinetic energy theorem, to solve for this here. So I'm going to do our work is equal to KE final minus KE initial. So KEF minus KEI. That's work equals FD cosine theta. Right? Plugged it into there. That stays the same. Work now. This change in kinetic energy, that's our work, is equal to this. Let's start plugging some numbers in. So this is 1/2 our m. We don't know what it is. That's what we're solving for. M. What's our final velocity here? 0. Minus 1/2 m. That's what we're solving for. What is our initial velocity? It's 8. Squared. This one should be squared too, but whatever. Equals, what's our force? 0.12. Our distance that we're traveling here is 45 meters. And our cosine of theta, all right? So the cosine of 180. Some of y'all are in a math class. You're walking around with these pie plates right now. Okay? And on that pie plate, somewhere on there, it's going to tell you what the cosine of 180 is. Okay? Or you can do it in your calculator. So what is 1/2 m 0 squared? Well, 0 times anything, this whole mess here is 0, minus 1/2 times m, 8 squared is 64, equals, right, 12 times 45 is 5.4. And what is the cosine of 180? If you've done it in your calculator, you know it's -1. All right, so keep moving on here. So I'm just going to do 1/2 times 64. I'll get 32. So 32m equals, that's an m, 32m equals -5.4. Now, that means that m equals 0.17, and since it's a mass, it's in kilograms.
-32.
I'm sorry, -32, because that's negative there. Difficult problem, yes. Something that you can all do, though. Thanks for watching.